Right, question 17, the spider question. Right, this was tricky. This is by far the trickiest question on the paper, I think. And as a consequence, not surprisingly, not many people got the marks here. But anyway, let's go through it. Well, I completed a free body diagram, free body force diagram for the spider. Remember, if you're drawing a free body diagram, a free body force diagram for an object, you only want the forces acting on that object. It really is that simple. So what do we want? Well, it's given us the one for the fly here. We want one for the spider here, don't we? Okay, so what forces are acting on the spider only? Right, so what do we got? Well, we've got the two tensions and the weight of the spider. So there's the spider there without its legs. Remember, free body diagram, you just need to draw a dot, a box, a square, anything. You don't need to draw an actual spider. So what do we got? We've got T1 going up. We've got T2 pulling it down. That's due to the weight of the fly pulling down. And then we've got, obviously, the weight of the spider as well. Now, we're going to say MS, small g. Okay, so there you have it. There's the three forces acting on the spider. Okay, and everything's in equilibrium at the moment. Everything's nice in equilibrium, so we need to set up our equations. So let's do the fly first. Okay, so let's do the fly. So for the fly, if you go back to the free body diagram, we've got T2 up, MFG down. So T2 going up has to equal the weight of the fly pulling down. So that's the fly. Now the spider, a bit more complicated. We've got T1 going up and T2 and MSG going down. So again, it's in equilibrium. So we've got T1 equals T2 pulling it down plus MSG, weight of the spider. Okay, so again, everything's in equilibrium. Those two equations have to be fulfilled. Okay, right, this is where it does get a little bit complicated. We need to think this through. The spider produces more silk, so the length of the silk above the spider increases rapidly, and the spider and fly both accelerate towards the ground. Assuming the mass of the silk is negligible, calculate their acceleration. Right, you have to, it doesn't actually give this assumption here in the question there, but we have to assume that the silk does not stretch. Okay, the only reason why the fly and the spider accelerates is because this length here is increasing rapidly. Yeah, it doesn't say that. I thought that was a bit harsh, but we have to make that assumption here. But the big one, the important one here is that both the spider and the fly accelerate at the same rate. Okay, because there's no stretchiness, there's no extension in the certainly in the silk that joins the spider and the fly. Okay, the only thing that's happening is this silk is not stretching. It's just been elongated because the spider is producing more silk. Right. We need to set up some equations. These equations would have been true if it was stationary. However, we need to tweak them now and equate them to MA, don't we? Okay. Right. So if it's accelerating, if the fly is accelerating, so what force have we got going down? Okay, so it's the MFG going down, isn't it? So if the fly is accelerating down, the resultant force, that's the weight, minus T2, is going to be equal to the mass of the fly times acceleration. Okay, so the fly is now accelerating downwards. For the spider, Okay, what forces are going down? With the T2 and the MSG. So now the spider is also accelerating down with the same acceleration. So T2 minus MSG, okay, minus, oh, hang on, T2 plus MSG minus T1. That's the resultant force on the spider equals mass of the spider times acceleration. Okay, so we have the same acceleration. The spider and the fly are both accelerating downwards at the same rate. We have MS, MF, and the two tensions. Now, what does it give us? What does it give us? It gives us T1. It gives us MS. It gives us MF, but it doesn't give us T2. So what do we do? Well, the eagle-eyed amongst you might see that we have a T2 there and a minus T2 there. So what do? We add those two equations together. If we add those two equations together, okay, if we add those two equations together, so adding this one to this one, this equation added to this equation, okay, the T2, the minus T2 and the T2 in the bottom both cancel out, they disappear, which leaves behind, what do we got? So we got mass of the spider, G, minus T1, plus the top one, MFG. Okay, that equals, what have we got on the bottom? We've got MSA. What have we got on the top? Plus MFA. So I've literally just added those two equations together. The reason why is because I noticed T2 is minus in the top equation, T2 is positive in the bottom one. Add the two equations together, T2 disappears instantly. So let's just tidy this up. Okay, let's tidy this up. Let's go big. Right, so what have we got? We've got the mass of a spider. Start again. We've got the weight of the spider, MSG, plus weight of the fly, MFG, all minus T1 equals MSA plus MFA. Again, same A. Now then, I do believe these values can be substituted in quite nicely. Okay. We tidy this up a little bit more. This becomes MS plus MF G minus T1. Again, we're given that equals MS plus MF A. Right, we are given that. We're given that. That's 9.81. We're given that. Given that. Easy peasy. Not quite. So that gives us an acceleration of 7.2. Okay. The spider question. Right, okay, yes. That's why we're all scared of spiders. Okay.